All right, first things first, I just want you guys to pay attention of what's going on this week and next week. So I put the big old announcement up there on your Canvas page. So right up here, this is just to remind you that your homework number 2 / test review number 2 is due by Friday at 3:30. You are to submit all answers in Canvas under the modules with the homework number 2 test review link. And you are to turn in the free response part, what I call part 2, of the homework number 2 test review by Friday at the review session. This also means that your test number 2 is going to be on Tuesday, February 27th. So just in case you didn't listen to me the last 3 times I've said this, now I've written it down on your Canvas site, which obviously makes it official. So there's that. A couple other things. You click over here on the modules and scroll down. Where are we at? Well, we're finishing up section 2.7 today, and we're moving on into section 2.8. So if you paid attention to your pre-section quiz stuff, your pre-section quiz is due 2.8. But let's take a look at what we're going to be doing the rest of the week so you guys have an idea. Homework set is due on Friday. I'm going to be finishing up most of section 2.8, if not the whole darn thing, today. Which means, what are we going to be doing on Thursday? Well, I could move on into chapter 3 if you wanted me to. Or I could take a day, since we're not going to have the review session like we normally do in terms of going over web work. We're going to be going over the homework set to prepare you for the test. I thought maybe I could just sit back and do some of those more interesting WebWork problems in terms of especially section 2.7, the ones with the right triangle trig and all that good stuff, which people love. So I thought maybe we could look at some of those, because I mean, we just hit or miss a bunch of problems that we do on the review sheet, and you see these guys really do come from the WebWork stuff. But that being the case, maybe I'll take Thursday and I'll do a bunch more problems based upon what you guys have questions for and stuff, and hopefully preparing you guys for the test. So, but I did do this. So if you look at your WebWork, WebWork 2.7 was actually due, what, tomorrow or something like that? Well, I pushed it back one more day, so now it's due on the 22nd, which is Thursday at 11:45 p.m., which means that if you don't get them all done and you have a particular question about one of them or 2 of them or whatever, I can actually help you guys out in classes on Thursday's class. You still got until 11:30 that night to get it submitted. And of course, the same idea on section 2.8. 2.8, I have that due actually on that Sunday, the 25th, because I don't want you guys sitting there still trying to work on WebWork problems when you should be working on the test. Your test is going to be on February the 27th, that Tuesday. Okay? Alrighty, and here's obviously the link for the homework number 2, and just to let you guys know, you click on this thing and you can read it, and there's, you can print one out, which you're supposed to. You're only going to be turning in the free response part, just like you did last time, and but I did make the whole thing into a multiple choice thing, so, or at least an area where you can just type in your answers in terms of the questions and stuff. And there you go, and here are the questions. But remember, just like last time, this is a computer thing. So I have the answers kind of programmed into this thing, but the Canvas does this random generator in terms of where these answers are going to actually be located at. So just because the answer is A on your homework set doesn't mean the answer is going to be the first one on this set. They do tend to kind of mix these things up and stuff like that. So just pay attention. And this is, again, remember what the ultimate goal of these review sets is to kind of give you guys a clue of what the test is going to look like. So you can kind of feel comfortable about, the format of the test and the like. So there we go. All right. Questions? Well, let's go ahead and get started. I still got a few more problems from section 2.7 to go over, which is the most important, and I can't do all the problems in the universe, but I can do most of them. So we will do my best at trying to do most of them. Now remember, I'm going to do the ones on the sheet here. There's some more interesting problems, especially when it comes to the trigonometry and the kite problem and things like that. But nevertheless, these are some good problems that we actually chose for you guys to actually do on the notes and stuff like that. And I will do more of them actually right off of WebWork on Thursday. That's what I decided to do with that. If you look at your syllabus, and by the way, can you actually view the syllabus thing now? The course calendar. I fixed it 3 times. Now it's got to be working at least one of these times. So hopefully you see that. And let me go back over here just to show you what I'm talking about. So if you go over here to your modules, okay, and at the top here, we have up here the, if I can find it, yeah, the course calendar. Tuesday, Thursday course calendar. Hopefully you can click on this thing and then click on this guy right here, and then you should be able to open it up. Because I think I found what my problem was when people couldn't see it. So, and here it is. And if you look at this thing, we are actually right on schedule, which is incredibly rare. All right, so, so if I tab this thing up and take a look at this guy over here, what is today? Today is February the 20th. We shall be covering the last part of section 2.7 and all of section 2.8. What is Thursday's class? Catch up and review. So I've decided I was going to do WebWork problems on that particular day. And of course your homework set is due on that Friday at the review session, which I hopefully will record. And then, which means your test number 2 is on Tuesday the 27th. So believe it or not, we are actually right on target for this particular stuff. So there you go. All right. Let's go ahead and get started on this one. Again, I stole this one off of WebWork Problem. So as I do these problems, you should be paying very close attention to the problems we do in class as compared to the problems we actually do in terms of ask you guys to do on WebWork. Here's one. Water pours into an inverted cone at a rate of 2 meters cubed per minute. If the cone has a radius of 2 meters and a height of 4 meters, find the rate at which the water level is rising when the water is 3 meters deep. Okay. Here's the first thing. Step 1, read problem. Step 2, read problem, draw a picture, which I went ahead and did for you, and start labeling some stuff. Now, water's being poured into this right cone, right here, inverted right cone, at 2 meters cubed per minute. That per means he's a rate, he's a derivative. Who is he the derivative of? Look at those units. This is physics. Meters cubed measures what? Cubic meters. Volume. So this would be dV over dt. Does that make sense? On this particular cone, they tell us that the original radius of the top of the cone, and I'll kind of bold this up here so you can see it, is 2 meters, and the height is 4 meters. The problem is the water is being poured into the cone, and here's your water level down here, and this is changing, so this is going to be called a variable, and this is the height of the water, so I shall call it h. This is the radius of the water, I shall call it r. With me so far? Now, we're talking about the volume of a right cone. So I need to come up with an equation that is the equation for whatever picture that I drew. This is a right cone, which we're talking about volume. And we all know that the volume of a right cone is equal to pi thirds, 1/3 pi r squared h. Things we know from SAT stuff. Also in that sheet, if you go look it up, volume of a right cone is 1/3 pi r squared h. Okay? So the first question always asks me, do we need to know these formulas for the test? You need to know these formulas for life. But if the harder ones, I will probably give you. On the test, I would have probably given you this one just to make sure that you didn't use something that was wrong and try to go calculate something off that. But there are some basic forms I do expect you to know. If I'm talking about the area of a circle is increasing, you should know what the area of a circle formula is. If I'm talking about area of a triangle, you should know area equals 1/2 base times height. Or the area of a circle is pi r squared h. I mean, there's some basic things you need to know just to graduate high school. So now you guys are in college. We still expect you guys to know this stuff. So this one, maybe not as much, but we do tend to see this one quite a bit. All right, here's my problem. What are we interested in? Find the rate at which the water level is rising. The water level rising is h. The rate of that means derivative, so we're looking for dH over dt equals what? When the water is 3 meters deep. The deep and the height of the water, same thing, when h equals 3 meters. That's the question right there. Find dH over dt when h equals 3 meters. I got a question for you. Did they tell me anything about the radius? In terms of rates of change of the radius? Because the radius of this thing is, as the water level rises, the radius is going to change as well. Did they tell you anything about dr over dt, the rate of change of the radius in this problem? No. So what we got here is we got a variable that they gave me very little information about. Here's the clue. When they do that on a word problem, there should be some mathematical way to eliminate the variable. So I really don't want to have r in this thing. I'm interested in h because the question is, what find dH dt, the rate of change of the height. So let's see if we can kind of basically plug in for this r in terms of h to see if we can come to a relationship. Now, I've done this trick before. I'm going to do it again. What do you see in this problem? Well, I see two triangles when it comes to, again, focusing on the height versus the radius. This is a right cone, so of the big one, the big radius of the cone is 2 meters. The height is 4 meters. But you also see a little triangle down here when we're actually talking about filling the cone up with water. And these are the variables that change. The height is changing and the radius is changing. And because triangle is embedded in another, what kind of situation do I have here? Similar triangles. And remember, the ratio of sides of similar triangles are equal. So therefore, I end up getting this. 2 is to 4, or 2 over 4, is equal to r over h. I'm going to cross multiply this thing, or actually I'm just going to multiply both sides by h. When I do that, I can clean it up. 2 divided by 4 is a half, times h is equal to r. Here the h's cancel. In other words, the way this cone is set up, the radius is always half the height. And I can use that information. So when I have volume equals 1/3 pi r squared h, I can go and take this r, which is equal to half h, and I can plug him into this equation and eliminate an r variable and convert him into an h variable. This tells me that volume equals 1/3 pi times r squared, but r is 1/2 h squared times h. Of course, you want to clean this guy up, so volume is equal to, well, let's see here, pi thirds. 1/2 squared is 1/4 times h squared times h. So this gives me volume, when you clean it up, is pi over 3 times 4 is 12. Pi over 12. H times h squared is h cubed. So I've got pi over 12, or 1/12 pi, h cubed is my formula for this example for the volume of the cone based upon h, which is the height of or the depth of the level of the water. But now here it comes. All that work was to get the formula in terms of variables that I know or want to solve for. Now what are we going to do with this thing once you get the equation? We do the same thing every time. We take the derivative with respect to t. So what's the derivative of volume with respect to t? Very good. dv over dt is equal to pi over 12 is a constant. Constants hold over. What is the derivative of h cubed with respect to t? 3h squared what? Very good. dh over dt. So you get dv over dt is equal to 3 goes in 12 4 times this. Pi over 4 h squared dh over dt. Now what's our goal? We know what dv over dt is. That's 2 meters cubed per minute. We want to find dh over dt when h equals 3. So plug in what you know and solve for what you don't know. So dv over dt was given to be 2 meters cubed per minute is equal to pi over 4 times h. H is 3 squared. and keep the dH over dt as the quote-unquote variable, because that's the dude we want to solve for. Well, let's clean this up. 2 is equal to 3 squared is 9 times pi over 4 is 9 pi over 4 dH over dt. I would divide by 9 pi over 4 so I can solve for that dH over dt. So this gives me dH over dt is equal to 2 divided by 9 pi over 4. But when I divide by a fraction, I'm going to invert and multiply. So this will be 2 times 4 over 9 pi. And 2 times 4 is 8. It's 8 over 9 pi. Now I'm going out of this thing being very elaborate on this guy. 8 over 9 pi. But I also want to go ahead and convert him into decimals. So I'm going to grab my handy dandy calculator over here. And with this kind of a problem, remember, when you're starting to have these pi's on this stuff, especially when the pi is in the denominator, you got to make sure you put parentheses around it. So parentheses around your denominator. So it'll be 8 divided by parentheses 9 pi. You understand? And I end up getting this one, which is equal to 0.28294212211. Okay? What would my units be on this particular problem? What would my units be? This is why we like the Leibniz notation. Blame the Germans, but you can at least read it. dH over dt. Height would be measured in what in this particular problem? Meters. And time is measured in minutes. So this would be meters per minute. Does that make sense? Meters per minute. Now, you think I'm being elaborate on this stuff, but question first.
Where does 3 go after you start plugging in? So you said so you have dv over dt equals pi over 4 times h squared. Where did the 3 go?
Times dH over dt.
Yeah, but like where did the 3 go for that one?
Okay, so we were given that the dV over dt is 2 meters cubed per minute. Our goal was to find dH over dt when the height was 3 meters. So height is a variable. We're trying to find dH over dt when the height was 3 meters. So I replaced the height with 3 meters.
Wouldn't it be 3 times 3 squared?
No. Okay. No. Okay, it's because way over here, I cleaned them up.
Oh,
When we took derivative, it's pi over 12 times 3, derivative of h cubed is 3h squared dH over dt, but 3 goes in the 12 4 times, and that's where the 4 came from. It's not a 12 down there, it's a 4. I cleaned up my fraction.
okay.
Does that make sense?
Yeah.
But the other thing is, I know I'm trying to be elaborate on this stuff, but I just want you to show you of why it's important to make sure you understand how to calculate this thing out. Because most people are going to type in the decimal answer. The answer was 8 divided by, and I made sure you guys understood how to type this in the calculator. When you got one of these pi's on this stuff, and the pi is in the denominator, you've got to put parentheses around it. 8 divided by 9 pi. And that was my answer. And I showed you that a few seconds ago. Well, what if I don't put parentheses there? 8 divided by 9 pi. Because a lot of people don't. They think, well, you do multiplication before division type thing. Well, no, that's actually not the order of operations. You do multiplication from left to right. What you're going to have here is 8 divided by 9 times pi, and you get 2.79 whatever. Well, what's the difference? Whether the bridge makes it to the other side of the river or not, whether people die or not. Because careless error will kill with this stuff. You've got to know how to use your calculator, computers, and all this other stuff to make sure that you calculate out a correct and accurate answer on this stuff. Parentheses are most important with these pi things here. Does that make sense? All right, just wanted to show you that. Don't lose you guys anywhere. And again, you got a WebWork problem very similar to this. The only difference between the WebWork problem that I wrote up here and the one that they have on WebWork itself is that they tell you in the problem that the diameter and the height are always the same. Well, that's a great equation. That means D for diameter is equal to H for height. But the problem is on this problem, what variable does your formula have in it? It has R, radius. So you've got to convert that over. Diameter is equal to 2 times radius, right? So you get 2 times radius is equal to height. which means radius is equal to height divided by 2. So in that problem, you would replace r with h divided by 2 based upon the given information they gave you. But again, the goal, so they did not give you anything about dr over dt and the rate of change of the radius, which means there should be a way you can eliminate this variable and just keep it in terms of the variables you are interested in. In this case, it's variable h. Does that make sense? All right, here's another one. A boat is being pulled into a dock by the means of a rope attached to a pulley on the dock. The rope is attached to the front of the boat, which is 7 feet below the level of the pulley. If a rope is pulled through the pulley at a rate of 20 feet per minute, at what rate will the boat be approaching the dock when 120 feet of rope is out? Now you know there's a WebWork problem just like this one. All they do is change a bunch of numbers. But the situation is still the same. Step 1, read problem. Step 2, draw a picture, label it. Okay? A boat's being pulled into a dock by the means of a rope attached to a pulley. Okay, so it's been a while since I've been to the beach, but I hear it's still there. So here, in case you didn't know, water. Okay, there you go. All right, and so we have a dock. In case you didn't know, I'll help you out. Dock, and we need a boat. So draw yourself a nice little boat. I used to be in the 3rd grade. The only kind of boat I can draw. If you're going to have a boat, let's have a boat. Throw some guns on that sucker and call it a battleship. Okay, there we go. Got radar. Oh, hold on, yards. There it is. Okay, I've got a boat. All right. And then, I didn't say it was a big boat. Okay, it's a small battleship. We'll call it a destroyer or something or other. So here is the pulley on the dock, and here is my dock worker right here. Okay, and he's cranking this thing out, because here's the bow of the boat, and through the pulley system, we're going to be cranking this thing in, and here's the rope that it does. There you go. Okay? So, a boat's being pulled into a dock by the means of a rope attached to a pulley on the dock. The rope is attached to the front of the boat, there it is right there, which is 7 feet below the level of the pulley. Well, here's my pulley right here. So if I kind of extend this thing over, and you'll see my nice little dotted line right here. This tells me that this distance from the pulley to the front of the boat, that is a distance of 7 feet, based upon the water level and obviously how big the dock is and stuff like that. So that's 7 feet. If the rope is being pulled through the pulley at a rate of 20 feet per minute, so here's my rope right here. That's being pulled at a rate of 20 feet per minute. So this is obviously going to be changing, so I'm going to give it a letter. I'm going to call Z the length of the rope. And if Z is the length of the rope, that makes that 20 feet per minute the rate of change of the Z of the rope, which is dz dt. At what rate will the boat be approaching the dock? So the boat approaching the dock. So here's the dock right here. I'm going to call this variable x. That'll be the distance that the boat is away from the dock. So what we're looking for is the rate of change of that distance between the boat and the dock. That's dx over dt when, so there's my question here, what is dx over dt when 120 feet of rope is let out? Rope is what variable? When z equals 120 feet. There's my scenario. What do you see in this particular problem? What do you see? I see a right triangle in which I'm interested in all the sides. I either know something or other, or it's a variable for all sides of the right triangle. Does that make sense? So what I've got here is I've got this 7, that's fixed. I've got z over here, and I got x over here. That's the scenario that's going on. Which means I got to come up with an equation. Being that I got all the sides of a right triangle here, obviously I'm going to use the Pythagorean theorem on this one, which would be x squared plus 7 squared equals z squared, or better yet, x squared plus 49 equals z squared. There is my equation. What are we interested in? We want to find dx over dt. When I see that something over dt, that tells me I want to take the equation of this guy, x squared plus 49 equals z squared. I'm going to take my equation and take the derivative with respect to t on this guy. What is the derivative of x squared with respect to t? 2x, very good, dx over dt, plus what is the derivative of 7 squared? 0. 7 squared is 49, and derivative of 49 is 0. It's a trick question. Equals, what is the derivative of z squared with respect to t? 2z dz over dt. Does that make sense? All right. Now, we want to find dx over dt when z equals 120. So dx over dt is the variable I'm going to keep in the problem, dx over dt. This is equal to 2 times z times dz over dt. So now let's plug in our numbers that we know. We want to find dx over dt when z equals 120, so we replace z with 120. dz over dt, I know what dz over dt is. That's how fast the rope is being pulled through the pulley, which is 20 feet per minute. And all I need now is to figure out what x is, plug it in there, and I can solve. Do you happen to know what x is? Of course not. I can give that to you. But you can go back and solve it. We know that x squared plus 49 equals z squared. We know that z equals 120, so x squared plus 49 is equal to 120 squared. So x squared plus 49 equals, and I'll put it in the calculator here, 120 squared, that would be what, 14,400? Yep, 14,400. I'm going to subtract 49 from both sides. So x squared is equal to 14,400 minus 49, which is now 14,351. And what is x going to be equal to? What kills off that square? Square root. And these are distances, so I always use the positive square root. 14,351. Square root of 14,351. That is what x is. Square root of 14,351. So 2 times the square root of 14,351 dx over dt is equal to, well, let's see here, 2 times 120 is 240, times 20 is 4,800. 4,800. So now I'm going to solve for dx over dt, and that would be equal to 4,800 divided by 2 times the square root of 14,351. And once again, I'm going to make sure you put a single term in the numerator so you're good to go, but you have 2 times the square root of 14,351. I need to put that in parentheses on this thing. So this will be 4,800 divided by parentheses 2 times the square root of 14,351. Close parentheses there, and I end up getting, I got too many zeros there. Oh, sorry about that. Got carried away. There we go. I got 20.03411,487, and it's a physics problem, so you've got to tell me what the units are going to be. What's the units on this particular problem? Well, what is distance? Dx over dt. X is a distance. What's distance being measured in? Feet per. What is time being measured in? Minutes. So it's being pulled into the dock at a rate of 20.03411,487 feet per minute. So it's going rather slow if you think about it. It's probably good because you don't want it kind of crashing. My battleship does not need to crash into their dock and clearly destroy it. Does that make sense? I'll let you guys know. Yeah?
The only question, how did you get the dz over dt to equal 20?
dz over dt equals 20. Oh, because up here, they say in the problem, quote, the rope is being pulled is attached to the front of the boat, which is 7 feet below the water level of the pulley. If the rope is pulled through the pulley at a rate of 20 feet per minute, rope is being pulled. Now the rope was attached to the pulley and the bow of the boat, okay? and it's being pulled through the pulley at a rate of 20 feet per minute, and that's in the direction of the rope. That means it's DZ over DT. Other questions? All right. Well, like I said, there are some other very interesting related rate WebWork problems for you guys. We didn't put them all on the little notes and stuff because we wanted you guys to at least attempt them first before crying, pain, and whining and moaning and whatever else you guys do about this kind of stuff, then going seeking help. Now on Thursday, I will go back over and I'll do like the last 5 WebWork problems or something like that to help you out, because some of them are rather interesting, especially the ones that have the trig on them with the kite being blown, and you want to figure out the angle of depression of the angle there, the rate of change of the angle of depression there of the kite. And so you know, we can talk about angles and trig. There's some interesting problems in there, but you'll notice what I do every time, and that is read the problem. I read the problem again, draw a picture and label it, and then I kind of come up with an equation, and then I take derivative with respect to time of that equation, and then I start chunking my numbers and solve for what I don't have, and then plug it in, and then solve for the question in the problem. I do the same thing every time. All right, last section before your test. Here it is, section 2.8. There are 2 topics in section 2.8. Linear approximation and differentials. Okay? Hopefully you'll watch the awesome pre-section video some idiot professor did for you guys on this thing, and you figured out basically what's going on here. Now, historically, this concept of differentials is what the great masters came up with to help them approximate. Because you got to remember, 400 years ago, they didn't use calculators and computers and the like. So it helped them approximate the change in whatever variable they're interested in. So, and then linear approximation is another mathematical way of approximating a particular function. And if you ever get in trouble on linear approximation, it's basically the same thing as the equation of the tangent line. Okay, but we use it to help us approximate stuff. And I'll try to show you some of that advantage, because I don't need a calculator to be able to approximate this stuff, but if I actually do it by hand and to calculate the exact value, I definitely will need a calculator. So here we go. All right, so first things first, the concept of differentials. We all know that the slope by formula is y2 minus y1 over x2 minus x1, which by formula is the change in y over the change in x, delta y over delta x. But when it comes to derivatives and that Leibniz notation, the slope of the tangent line is my derivative dy over dx, which means that the slope delta y over delta x is approximately the same thing as the dy over dx, the derivative, if you actually insert a particular point. So from this right here, we also know that the derivative dy over dx can also be written in that Leibniz notation as f prime of x. So in other words, okay, we have this dy over dx equals f prime of x. And if I take this thing right here and I treat dy separately from dx, and I actually solve this equation for the dy, which means I multiply by dx on both sides, you get a formula. Dy is equal to f prime of x dx, where, because of this statement right here, dy approximates delta y, and dx approximates delta x over here. This is the idea of breaking up my fraction. Delta y over delta x is approximately dy over dx, which means delta y is approximately dy, and dx is approximately delta x. But if we take the derivative notation and solve for dy, dy is equal to f prime of x dx. This right here is the formula for the differential. This we would say is the differential of y. dy is called the differential of y. Now, what's the big deal? This differential of y called dy, this dy, squiggle equal to means approximates delta y, the actual change in the y coordinate. Okay? But The differential of y is nothing but a formula. So if you watch the awesome pre-section video, I did this problem and this problem right here. Well, I ask you, hey, what is the differential of y, or in this case, the differential of f, because the function had a name. We called him f of x, so it's the differential of f. So here we go, right here. Let's pick it up. And again, pay attention to the directions. What's the directions? It says this. Find the differential of y. Those directions. Calculate for me a formula for the differential of y. But notation is everything. This is y equals 5x cubed. So remember, the differential of y by formula is the derivative of my function, whatever that function happens to be, with a dx put at the end of it, times dx. This is the differential formula. So in this particular example, the differential of y would be equal to, what is the derivative of 5x cubed? 15x squared. And then you stick times d, whatever that independent variable is. This was an x, so you times dx. Does that make sense? And there's the answer. They didn't ask me to do anything with it. They just want to know what's the formula for the differential of y. Well, in this first problem, it's 15x squared dx. What about the second problem? I got y equals 3x squared plus 4x minus 5 divided by 5 times the sine of 2x. What's the differential of y? Well, no problem there. Here we go. The differential of y is equal to, bracket, the derivative of this thing. What rule would you use to take derivative of 3x squared plus 4x minus 5 over 5 sine x plus 2x? What was it? Quotient rule. That's just practice getting ready for your test. Derivative the top times the bottom minus the top times derivative the bottom all over the bottom squared. Just try to do a problem and make you practice. Derivative the top. What's the derivative of 3x squared plus 4x minus 5? 6x plus 4. The derivative of the top times the bottom, 5 sine of x plus 2x. Derivative of the top times the bottom minus the top, 3x squared plus 4x minus 5 times the derivative of the bottom. What's the derivative of 5 sine of x? What's the derivative of sine? That'd be 5 cosine of x. What's the derivative of 2x? So that'd be plus 2. All over the bottom, 5 sine of x plus 2x squared, the bottom squared. That's nothing but the derivative. And if you put this thing down, it's a 10-point problem. We may have to just give you 1 point and take off 9 points, because you at least took the derivative right. But it's not the differential. What does the differential have with it? Times d, whatever the independent variable is. The independent variable, once again, in this problem is x, so you got to put times dx in the back of it. That's the differential. Does that make sense? All right. So, turn back. Whole point of this differential stuff is this, to try to give you guys a visual perspective of why this stuff is needed and with the application of it. As I mentioned to you a few seconds ago, delta x is approximately dx. Delta y's can be approximated by dy here. But what exactly is delta x? Delta x is the change in x. So if you go from x to x plus delta x, the amount of change between these 2 points is delta x. What exactly is delta y? Well, if you plot x through this whatever function you have now, you plot it. Here is x. You plot it. There's f of x. Here is x plus delta x. When you plot it, here is f of x plus delta x. What delta y is the change in the y coordinates. So this delta y is the change in the y coordinates, top minus bottom. The top one is f of x plus delta x, minus the bottom one is f of x. It's the change in the y coordinates. Okay? But what we're going to be trying to do here is this. We can calculate this thing right here, but it can be a royal pain. You know, we got some kind of function, and I want to know when x is going between 1 and 1.1, what would the change in y actually have in it? How much is the change in y? Well, we can give you the exact value of the change in y, but the goal here is to use the differential. Differential of y And this is going to approximate that delta y. But the differential of y is the derivative of my function times dx on the back of it, where remember dx and delta x are pretty much the same thing here. So I could actually, instead of trying to crunch this type of mess out, I can crunch this type of mess out and get a little bit better answer in terms of easiness without a calculator. So let me give you an example here. Now, I did this example actually on the video, so please go back and watch that thing. But tell you what, I don't know if all you people have watched this one, and I got time, so let's do this problem again. All right, use differentials to approximate the change in area when going from 4 to 4.2 feet. Okay? We want to use differentials. So we want to know what the change in area is. So using differentials, the change in area is dA. But remember, what is my formula for differential? It's a formula. dy is the derivative of my function times dx. That's the differential formula. But this is when x is the independent variable. We're talking about change in area of a circle, and they gave that to me to be pi r squared. A is area. What does r stand for? Radius. Right here you're going to see people that are very knowledgeable and do real well in calculus somehow cannot pull out 100 on this thing because they don't pay attention. So watch this. So I'm going to take my derivative of area times d. What was that independent variable? It's not x. There's no x's in this problem. What's the independent variable? R. So my differential for a is going to be the derivative of pi r squared. What's the differential of pi r? What's the derivative of pi r squared? Pi is a constant, leave it alone. Derivative of r squared is 2r, so you get 2 pi r times dr. That is the formula for the differential. How many times have I had students on the test? Area equals pi r squared. What is the differential of area? 2 pi r dx. That tells me you weren't paying attention. What's the variable? There's no x in this thing. R is the variable, or whatever the other variable. We like to do a lot of t's in this class because of physics, dt and things like that. But no, in this variable, this function, r is the variable. All right, so there it is. Now, here's the deal. R is equal to 4 feet. That's where we started from. What I need to calculate is what the change in R is. Here's your formula for the change in R. It is R new minus R old. So my change in R is equal to the R new is 4.2 minus R old is 4. So honestly, how much did my R change? 0.2 of a foot. Now delta R can be negative, but we're going from 4 up to 4.2. This is a positive move. Does that make sense? And remember, delta R is approximately the same thing as dr, and that's still going to be 0.2. So I've got R being 4 and dr being 0.2 for the amount of change in R, and all I'm going to do here is just plug in my number. So dA would be equal to 2 pi times R, but R is 4, times dr, the change in R, and based on the data is 0.2. So let's do some math here. I've got 2 times 4. What's that? 8 times 0.2. Well, 8 times 2 is 16, but 8 times 0.2 is 1.6 pi. Notice I'm not using a calculator on this thing. What would my units be? Because it does have units. Well, it's dA. What does A stand for? Area. Distance is measured in feet, so this would be feet squared. Don't tell me per anything. This is not a derivative. This is a differential. It's just the dA part. There's no over dt, no crap like that. It is just dA, which will have the same units as A does. In this case, feet squared. Does that make sense? Now, I mean, if you really wanted me to multiply this out, I could use 3.141599269 and multiply it by 1.6. I can do that by hand, but clearly you guys don't pay me enough for that. So we're going to use the calculator for this one, 1.6 times pi, just to show you what I get. I got 5.026548246 feet squared. Because there's a part B to this problem. Find the actual change in area when going from 4 to 4.2 feet. So the actual delta A, change in area, is going to be the area at R new minus the area, in this case, when R old. So this will be the area when R equals 4.2 minus the area when the original R, which was equal to R radius was 2 feet. 4 feet, sorry. 4 feet. Again, area is equal to pi R squared. So this would be pi times 4.2 squared minus pi times 4 squared. Which is really, you can factor out pi. That leaves you with 4.2 squared minus 4 squared. Well, this is a pain. I guess I could probably do it if you really asked me enough, but I'm just going to put the answer here on the calculator, parentheses 4.2 squared minus 4 squared, and then I'm getting 1.64, and don't forget to put the pi back on there. So my actual change in area is 1.64 pi. What would that units be? Feet squared, or go on a decimal, 1.64 times pi is 5.152211952 feet squared. Does that make sense? Now, the whole idea behind differentials is the differential of A should approximate delta A. And notice 1.6 pi is what I got with the differential. When I actually did it out by hand for the exact change in area, I got 1.64 pi, which means I got the exact area was 1.512 and the approximate was 5.0265. You know, it's very, very close. It's going to be off a little bit, but if estimation is good enough, the differentials are a lot easier to use than actually trying to calculate the exact area, especially when your formulas become a little bit nastier. Does that make sense? This is the idea. So here's another problem. If y equals x cubed, calculate delta y for x equals 2 to x equals 2.01. So we're going from 2 to 2.01. They don't have any units on this thing, so that's fine. But we want to calculate delta y. Delta y would be the exact change of y at x new, these are the formulas you need to know, minus y at x old. So my delta y would be the y of x being equal to 2.01 minus y when x was equal to 2. Now remember, in this problem, y equals x cubed. So my delta y would be 2.01 cubed minus 2 cubed. Well, thank God for calculators, but the 20th century, the 17th century type of mathematician would actually have to multiply 2.01 times 2.01 times 2.01 to get the wonderful 8.120601. We could have done that, but I used a calculator. This one I don't need a calculator for. What's 2 cubed? 8. We can handle that kind of math. So what is 8.120601 minus the 8? That is 0.120601. That is the exact change in y coordinate. It is 0.120601 units, if you will. But I had to use a calculator to get this thing out because it's a pain. Now watch this. Now calculate delta y for x is going between 2 and 2.01. Remember, delta y is the derivative of your function times d, whatever the independent variable is. Remember, y is equal to x cubed in this problem, So your independent variable in this example is x, so times dx. Okay? So the differential would be, all right, don't hurt yourselves, what's the derivative of x cubed? 3x squared times dx. Now to calculate the differential, you've got to have x old, because that's what you plug in, the original x, which was 2. And you also need to calculate delta x. Delta x by formula is x new minus x old. The x new is 2.01. The x old was 2. That gives you 0.01. That is what delta x is. Remember, delta x being equal to 0.01 is what we're going to plug in because it approximates what the dx is. So dx is going to be 0.01. X old is 2. So we're going to plug in x is 2 and delta x, or dx, excuse me, is 0.01. So here we go. dy would be 3 times x squared times dx. Plugging in x was 2 and delta x is 0.01. Now envision yourself in the 17th century, 18th century, early part of the 18th century, 1700, 1710, 1720. What is 2 squared? Times 3? 12. So your dy is 12 times 0.01. What is 12 times 0.01? Well, I just moved the decimal place 2 places left. I get what? 0.12. There is what this guy is. And as a check, the delta y should approximate, the dy, the differential y, dy, should approximate the delta y. And what do we get when we plugged it in? I got 0.12 with no calculator, but when I actually found out the change in y, I got 0.120601, had to use a calculator to get all that good stuff, but you'll notice, yeah, they're pretty darn close to each other. And if approximation is good enough, this was a much better way of doing it because you didn't have to hurt yourself. And I didn't use a calculator like they would have not used in the 17th century. Does that make sense? So here's another problem. Volume of a sphere, things we have memorized from high school, is 4/3 pi r cubed. Use differentials to approximate the change in volume when going from r equals 3 to r equals 2.8. Okay? So, here we go. R old was 3 feet. R new, we moved it down to 2.8 feet. So my change in R by formula is going to be R new minus R old. Order matters. So R new is 2.8 minus R old is 3. So what is 2.8 minus 3? Very good. Negative 0.2 feet, which is what we're going to be plugging in for dr. dr is negative 0.2. Now, remember, the differential of volume is going to be the derivative of your volume function times d, what the independent variable is. Look at your formula. The formula of volume equals 4/3 pi r cubed. What's the independent variable in this problem? R. Not an x. It's an R. Okay? So my differential is going to be the derivative of my volume equation. What's the derivative of 4/3 pi r cubed? Well, 4/3 pi is a constant, leave it alone. Derivative of r cubed is 3r squared. And 3 times 4/3 makes just the 4 pi times r squared. That's my derivative. Times dr. Does that make sense? You have to come up with a differential form first. This is the formula for the differential of volume of the sphere 4/3 pi r cubed. But now let's calculate it out. When you plug into this thing, you plug the original R old into it, the original R. So your differential is going to be 4 pi R, the original R, which was 3 squared, times negative 0.2. Well, here we go. 3 squared, 9, times 4, 36. So So 36 pi, and I'm going to do this for your benefit, 36 pi times a negative 0.2. So my differential is going to be a negative, because positive times negative is a negative. What is 36 times 2? 72. So what's 36 times 0.2? Very good, 7.2 pi. And what would my units be? It's the differential of volume. Distances are measured in feet, so therefore what would volume be measured in? Feet cubed. And this is the answer, and notice I did not use a calculator for this. Okay? Not yet anyway. Now I want you to see what's really going on here, but that's my answer. And so when I actually plug that in on the calculator using the pi 3.14159269 button on this thing, I'm going to get this, negative 7.2 times that pi button. I just want to go with the decimals. Negative 22.619466711 feet cubed. Now, the second one asked me to do this. Find the actual change in volume. The actual change in volume would be the volume at R new minus the volume at R old. Does that make sense? So this would be the volume when R equals the R new volume, new radius was 2.8, minus the volume at R equals, the old one was originally 3. So remember, this is the volume of a sphere. Volume is equal to 4/3 pi R cubed. So this would be 4/3 pi times R, which is 2.8 cubed, minus 4/3 pi times 3 cubed. So if you want to clean this up, this is 4/3 pi times 2.8 cubed minus 3 cubed. 2.8 cubed is 2.8 times 2.8 times 2.8, okay? And 3 cubed is 27. But these are kind of crappy numbers, so I'm going to put them on the calculator. 2.8 cubed minus 3 cubed leaves me with 4/3 pi times negative 5.048. And if I multiply that number times 4 and divide it by 3, I end up getting 6.730666667 pi feet cubed, but negative, don't lose the negative there. But here's the thing, I want to really compare these numbers, so I'm just going to multiply that times pi and see what I get. I got negative 21.14501295 feet cubed. That's the actual change in volume, and basically, look at this thing. The entire problem, after I typed into the formula, I had to use a calculator to crack this out, unless I want to be here for at least 2 hours trying to crunch these crappy numbers out. But look at this. This is the differential. It's going to approximate this. This is the actual change in volume, negative 21.14. Using the differential, I got negative 22.6. They're close. They're not going to be exact, but they're going to be close. And if approximations do, the differential is so much easier to calculate. Yeah.
Can you say we're not going to have a calculator on this test?
No, yes, I said no calculator on this test. For you guys, no calculator on this test. You guys had calculator on the first test, so I can't give you a calculator on every test, so we'll just not have a calculator on this test.
They're gonna be like nicer numbers than probably.
Well, I got a question for you. Could you do that one without a calculator?
Yeah, probably.
Yeah, probably. Worries me. Yes, sir, I can. Would be even better. Good. Yes, okay, good. So that's the kind of answer I would ask. I'm not gonna make you do this. I will give you nice numbers. I'm not gonna go from, honestly, I can let you know right now. If I'm gonna do a differential, you're gonna go from R equals 2 to R equals 2.1. So what's your change in R? 0.1, easy math to multiply, that kind of thing. Yeah. So don't worry, if I'm not gonna give you a calculator, I'll outthink the problem such that you don't have to hurt yourself so bad on this thing. Does that make sense? All right. Well, the second concept in this section, the last concept in this section, the last section, 2.8, before your next test, is linear approximation. Now, we all know, and here's the idea behind it. I got a nice little function. And out of this little function, I'm interested in what's going on right here when x equals a. So I approximate this thing, I plug it in. Here's a, I plug it into my original function, which is this curve right here, and I get f of a. There's my point. What we're interested in is find the equation of the tangent line. You guys have been programmed personally by me. Anytime you need to find the equation of the tangent line, what's the equation of a line point system that I'm always going to use? Point slope. Y minus y, okay, 0, equals slope of the tangent times x minus x0. Point slope. So I've got my first point. My point is a f of a. And that's what I said. A is x naught, f of a is y naught. So I replace y naught with f of a. I replace x with a. And what's the slope of the tangent line? Once again, you've been programmed personally by me. The slope of the tangent line is the derivative function evaluated at my point x naught, which is the same thing as f prime of a. So the slope of the tangent line is my derivative evaluated at a. So I replace slope of the tangent line with f prime of a. So I get, when I clean this up, I get y minus f of a is equal to my derivative of a times x minus, minus a. So f prime of a times x minus a. And if I want to solve for y, I add f of a to both sides. And I get a formula. Y equals f of a plus f prime of a times x minus a. But, listen to my words. This is the standard equation of the tangent line. We're going to be fancy about this. We're going to start using these equations of a tangent line to approximate, so all this section is about approximation, to approximate functional values at really nice crappy points. So, here's the deal. When you hear the word linearization, let's think about the root word for linearization. What do you think of when you think of the word linearization? Lines. I think of lines. And the linearization of a function is the same thing as the equation of the tangent line. But they're going to be fancy about it. So instead of calling him y, they're going to call him L of x. L for linearization. So the linearization of x is equal to f of a plus f prime of a times x minus a. It's the equation of the slope of the tangent. It's the equation of the tangent line. Well, we're going to call this linearization because here's the deal. This is the idea. You see this problem right here? See that function? It's really crappy. Very crappy. Here is the linearization equation. It is L of x is equal to f of a plus f prime of a, some kind of number, times x minus a. I would like to approximate what a point something or other is. I want to be a little bit off of a. I want to be near a, because a is my centering point. I got two options. I can plug a point something or other into my function, but you know that's going to be really nasty when we start taking the cosines and the sines and cubing them and then squaring them and then dividing by crappy numbers and stuff like that. This can be very painful to plug in this number, especially without a calculator. But instead of typing it into the original function, if close is good enough, I can type it into the linearization equation. It's going to be a little bit off, but look, f prime of a is just kind of a derivative number. It's a number. When I plug in a point something minus a, I get point something. I take point something times the slope and then add it to f of a, whatever that y coordinate was, and that's going to give me a very close approximation to what f of a point something or other was originally. That's the whole idea. We're going to come up with the equation of the tangent line, but this is so fancy, we created a formula for you to memorize for the linearization equation, and it's used to approximate crappy functions if approximation is good enough. Now, once again, hopefully you'll watch the awesome pre-section videos because I've done these two problems for you guys already. So let's come over here and do this one. Find the linear approximation of f of x equals the cosine of phi of x at a equals pi halves. Oh, we threw trig at you. Oh no. You hear the word linear approximation or the word linearization, you have a formula. You know what the formula is? It is L of x is equal to f of a plus f prime of a times x minus a. There it is. Linearization. So here we go. A is pi halves. So the first thing I want to do is know that A is pi halves. I want to do f of pi halves. That would be the cosine of 5 times pi halves. That's the cosine of 5 pi halves. What is the cosine of 5 pi halves? Well, let's go back and look at it. Here's the old unit circle. Here's 0, here's pi halves, here's pi, here's 3 pi halves, here's back to 2 pi. Pi halves, pi, 3 pi halves, 2 pi. What comes next? 5 pi halves. 3 pi halves and 5 pi halves are the same angle except 5 pi halves has an extra loop in it. What's the cosine of it? Very good. Because this is, the point you're going through is the point 0, 1. Cosine is the x-coordinate. The answer to this problem is 0. The cosine of 5 pi halves, which is the same thing as 90 degrees, is 0. Okay? So f of pi halves is 0. The next thing I need to know is what the derivative is. Remember, your function is the cosine of 5x. What would your derivative of this thing be? Well, what's the derivative of cosine? By the way, it's chain rule. Derivative outside, inside stays the same time derivative inside. Derivative of cosine is negative sine, the inside 5x stays the same, but then chain rule. Times the derivative of the inside. What's the derivative of 5x? 5. So f prime of x is actually negative 5 sine of 5x. So f prime of pi halves is going to be negative 5 times the sine of 5 times pi halves. So this is negative 5, but what is the sine of 5 pi halves? Well, we calculated them a few seconds ago. Here's 0, here's pi halves, pi, 3 pi halves, 2 pi, 5 pi halves is back up here. But what's the sine of it? Remember, sine is the y-coordinate of these unit circle answers, which is 1 times 1, and 5 times negative 1 is negative 5. Does that make sense? So, by linearization, centering it at pi halves is going to be f of pi halves plus f prime of pi halves times x minus pi halves. Now, let's plug in what we know. By linearization is equal to, what is f of pi halves? We calculated that a few seconds ago, and what did I get? 0. Plus f prime of 5 halves is negative 5 times x minus pi halves. So your linearization would be negative 5 times x minus pi halves. You can leave it like that, or if you really, really wanted to, you could distribute, make it look like something or other. And I tell you both because I never know how they're going to put them on multiple choice kind of tests. So I'm going to distribute. This gives you negative 5x plus 5 pi halves. And so, here's the idea behind it. All right. Pi halves is the number 1.5707 whatever. Okay? Now, that's my centering point. Linearization is used to approximate a particular function of any point that is near the a value. If you go farther down the road in a, your approximation may be bad. But anywhere near a, this is going to be a good approximation. Because I got a question for you. What if I want to do, how about 1.58? I want to know what is the cosine of 5 times 1.58. 1.58 is very close to pi halves, 1.5707. I got negative 0.0640060021256. You with me? But instead of plugging in this, because how in the world does the calculator do that? Well, we're going to talk about programming eventually. How does the calculator give me this answer? Does it have cosine somehow memorized in the computer banks of the calculator? No, there is no computer bank of the calculator. It's doing a trick. And one of the tricks is this concept of a style of linear approximation. It's actually called a Taylor polynomial. I'll get there when I get you to Calc 2. But, watch this. Instead of plugging it into this function, let me plug it into my linearization. It's -5 times an x I'm plugging in was 1.58. And then add that to 5 pi divided by 2. And you know what you get? Something very, very close. And this is the whole purpose of linearization. Instead of trying to do, I mean, this is a transcendental function. It's cosine. Who wants to, by hand, calculate some crappy cosine of something or other? Especially if it's not an exact value of things we have memorized like pi 6, pi thirds, pi halves, and stuff like that, pi fourths. If I got to do crappy numbers, it's better to plug it into the linear approximation. It's a lot easier to do. So, take a look at this next guy. Do one more and then I'll let you guys go. Use linear techniques to approximate. Now this is a problem they're making you guys think. It's real easy, but here's the deal. We want you to approximate the square root of 16.1. What you're going to have to do here is you're going to have to think what is your function going to be and what is your A point. And remember, A is what I call the good point. First off, figure out what the function is. You're trying to take the square root of 16.1. What function are you doing? Square root. So f of x would be the square root of x. That would be my function. Now we're trying to do 16.1. Can you think of a number very close to 16.1 that you could actually do a square root of? A would be 16. That would be the good point near the value they were trying to approximate. Does that make sense? So what we're going to do here is we're going to do linearization of this guy with this information. Linearization is f of a plus f prime of a times x minus a. A is 16. That's a good point near that 16.1. So here we go. F of a. F of 16 is going to be the square root of 16, which is 4. So my linearization equation will be f of 16 plus f prime of 16 times x minus 16. F of 16 is 4, so my linearization equation is going to be 4 plus. Now I need the derivative. Remember, I don't do square roots. So square root of x is the same thing as x to the half. The derivative of this would be 1/2 x to the negative 1/2. When you clean it up, that's 1 over 2 square root of x. So f prime of 16 is going to be 1 over 2 times the square root of 16. What's the square root of 16? 4 times 2 is 8. It's 1/8. So this is going to be 1/8 times x minus 16. This is my linear approximation. Now I'm going to show you what the great master did. Do you guys happen to know what the decimal version of 1/8 is? 1, 2, almost 5. 125 is what 1/8 is. Times x minus 16. Now, to approximate the square root of 16.1, the x that you're plugging in is 16.1. Squiggly equal to means approximate. Instead of trying to do it with 16.1, plug 16.1 into your linearization equation. Look at the way I wrote it. It makes it easier on the math. This will be 4 plus 0.125 times 16.1 minus 16. You with me? We'll do the arithmetic. This will be 4 plus 0.125. What's 16.1 minus 16? 0.1. That'll be 4 plus, what's 0.125 times 0.1? 0.0125. So you know what you get for the linearization of 16.1? 4.0125. Does that make sense? But wait. What is the square root of 16.1 according to the calculator? 4.0124853. This is going to be a very close answer to this. Does that make sense? But it approximated it. Does that make sense? And that's kind of the whole point of this linear approximation. I still have, and I'll do this next time, the last couple of problems on section 2.8, and then we'll do WebWork problems on Thursday. So see you guys then.